Today's topic is transformation of charge and current densities and current 4 vector. In Minkowski space, which is 4-dimensional space, current density J and charge density rho are grouped together to form current 4 vector J mu, as J mu equal to J vector and I C rho. So current 4 vector J mu have 3 components of current density J vector, Jx, Jy, Jz, and fourth component is related to charge density rho, and fourth component is IC rho. So this is current 4 vector J mu. 3 components are J vector, Jx, Jy, Jz, and fourth component is IC rho. Consider a volume element d tau equal to dx1, dx2, dx3. If rho is charge density, then charge in this volume element dq is given by dq equal to rho dx1 into dx2 into dx3. This is the definition of charge density rho. Charge density rho is charge upon volume, charge per unit volume. So charge dq in volume element dx1, dx2, dx3 is equal to charge density rho multiplied by this volume element dx1, dx2, dx3. Multiplying this equation by a 4 vector dx mu. X mu is position 4 vector. So if we multiply this equation for dq by 4 vector dx mu, we get dq into dx mu equal to rho dx1, dx2, dx3 into dx mu, and we write it as rho dx mu upon dt into dx1, dx2, dx3 dt, multiplying and dividing by dt. As charge is invariant, dq is invariant, and dx mu is 4 vector, so left hand side of above equation is a 4 vector. So right hand side of this equation must be a 4 vector. Further, we know that 4-dimensional volume element is Lorentz invariant, that is dx1, dx2, dx3, dx4 equal to invariant. This is 4-dimensional volume element. Here x4 is ICT. So we have dx1, dx2, dx3 into dt equal to invariant. So in this equation 2, in right hand side, this term dx1, dx2, dx3 into dt, it is Lorentz invariant. So the remaining term in right hand side, that is rho dx mu upon dt, that must also be Lorentz invariant. Therefore, the right hand side of equation 2 to be a 4 vector, rho into dx mu upon dt must be a 4 vector. Let this 4 vector may be represented as J mu equal to rho into dx mu upon dt. This is current 4 vector. J mu equal to rho dx mu upon dt. First component of this 4 vector is J1. J1 is rho dx1 upon dt, that is rho dx upon dt. Dx upon dt is u1, x component of velocity. So J1 is rho u1, similarly J2 is rho u2 and J3 is equal to rho u3. And fourth component J4 is rho dx4 upon dt and x4 is ICT, so it is IC rho. Now for current 4 vector, these are the 3 components J1, J2, J3, which are rho u1, rho u2, rho u3. We write these 3 components as J vector. And fourth component J4 is IC rho, which is related to charge density rho. So J mu, which is equal to J vector and IC rho, it is a 4 vector known as current 4 vector. It transforms under Lorentz transformation as J mu dash equal to alpha mu nu J nu. It is the definition of 4 vector, a set of 4 quantities J mu which transform according to this relation, then it behaves as 4 vector. So if J mu is 4 vector, then it transforms under Lorentz transformation by this relation. J mu dash equal to alpha mu nu J nu. J mu dash is this column matrix having 4 components J1 dash, J2 dash, J3 dash, J4 dash. And alpha mu nu is this square matrix having 4 rows. First row is gamma 0 0 I gamma beta. Second row is 0 1 0 0. Third row is 0 0 1 0. And fourth row is minus I gamma beta 0 0 gamma. And then J nu. J nu is this column matrix having 4 components J1, J2, J3, J4. From this relation, we can find the expressions for J1 dash, J2 dash, J3 dash and J4 dash. J1 dash from this equation will be equal to gamma J1 plus I gamma beta J4. Multiply first row of this square matrix with this column. We have J1 dash equal to gamma into J1 plus I gamma beta into J4. So J1 dash becomes equal to gamma J1 plus I gamma beta J4. Gamma is taken common, so it becomes gamma into J1 plus I beta J4. Put beta equal to V by C and J4 equal to IC rho. And now I into I, it is I square, that is minus 1. So the second term in right hand side becomes minus V rho. So we have this relation J1 dash equal to gamma into J1 minus V rho. Similarly, other relations are J2 dash equal to J2 and J3 dash equal to J3. And for J4 dash, we have J4 dash equal to minus I gamma beta J1 plus gamma J4. This is the fourth relation for J4 dash. J4 dash equal to minus I gamma beta J1 plus gamma J4. Gamma is taken as common, so it becomes equal to gamma into J4 minus I beta J1. And J4 dash is IC rho dash and J4 is IC rho. So we have this relation IC rho dash equal to gamma into IC rho minus I. Here we put beta equal to V upon C and then J1. If we divide this equation by IC, we find the expression for rho dash as rho dash equal to gamma into rho minus V upon C square J1. These are the transformation equations for current and charge densities. So we have this current 4 vector J mu having 4 components. 3 components are in this J vector and fourth component is IC rho. And as it is 4 vector, it transform under Lorentz transformation by this relation J mu dash equal to alpha mu nu J nu, and then we can find out these 4 relations for J1 dash, J2 dash, J3 dash and J4 dash, and these are the transformation equations for current and charge densities. Now we consider electromagnetic vector and scalar potentials. We will define what is electromagnetic vector potential and what is electromagnetic scalar potential. In a region of charge density rho and current density J vector, Maxwell's field equations are, these are 4 Maxwell's field equations: electric field E vector and magnetic field B vector. So for electric field E vector and magnetic field B vector, we have these 4 relations known as Maxwell's equations. First equation is del dot E equal to rho upon epsilon 0. Second is del dot B equal to 0. Third is del cross E equal to minus delta B upon delta T. And fourth is del cross B equal to mu 0 into J plus epsilon 0 delta E upon delta T. Here E vector is electric field vector, B vector is magnetic field vector, epsilon 0 and mu 0 are permittivity and permeability of free space. These are 2 constants, epsilon 0, which is known as permittivity of free space, and mu 0, which is known as permeability of free space. Rho is charge density and J vector is current density. So remember these 4 Maxwell equations. First 2 equations are for divergence of E and divergence of B, and third and fourth equations are for curl E and curl B, del cross E and del cross B. These are curl E and curl B. del dot E and del dot B. These are known as divergence E and divergence B. As divergence of curl of any vector A vector is always 0, that is del dot del cross A is equal to 0. Del dot means divergence, del cross means curl, del cross A means curl A. So divergence of curl of any vector A is always 0. Del dot del cross A is 0. Then from this second relation, second Maxwell equation, del dot B is 0. So we can write B vector as del cross A, because del dot del cross A is 0. So from this second Maxwell equation, del dot B equal to 0, we write B vector equal to del cross A. A is known as electromagnetic vector potential. So A vector electromagnetic vector potential is defined as B equal to del cross A. It is related with magnetic field B. Now substituting the value of B from this equation in equation 3. This is equation 3, third Maxwell equation, del cross E equal to minus delta B upon delta T. So del cross E equal to minus delta upon delta T, and we write B equal to del cross A. And we write this as del cross, and inside bracket we write minus delta A upon delta T. There is one operator, delta upon delta T, is differentiation with respect to time, and second operator is del vector. Del vector having components delta upon delta x, delta upon delta y, delta upon delta z. It have three components which are differentiation with respect to x, y and z. So x, y, z and t are independent with each other. So we can exchange these two operators. So we write del cross minus delta A upon delta T. In left hand side we have del cross, in right hand side we have del cross. This del cross is taken as common. Right hand side term is bring in left hand side, and del cross is taken as common. Then we have inside the bracket E vector plus delta A upon delta T equal to 0. Del cross E vector plus delta A vector upon delta T equal to 0. Del vector means curl. As curl of gradient of any scalar phi is always 0, del cross del phi is always 0. Del phi is a scalar quantity. If phi is any scalar function, then del phi is gradient phi, and del cross del phi is curl of gradient phi. It is always 0. So from this relation, del cross E plus delta A upon delta T equal to 0. As del cross del phi is 0, then this quantity inside the bracket can be written as gradient phi, and we write it as equal to minus del phi. So we write E plus delta A upon delta T equal to minus del phi, because del cross del phi is always 0. This gives E vector equal to minus del phi minus delta A upon delta T. So this define phi. Scalar phi is known as electromagnetic scalar potential. Electromagnetic scalar potential phi, it is related with E vector, electric field. phi and A vector both are related with E vector, and this is A vector scalar potential, electromagnetic scalar potential, electromagnetic vector potential A vector, B equal to del cross A. Here A is electromagnetic vector potential, it is related with B vector, and here in this expression A vector and phi both are related to E vector, electric field. So these are the definitions of A vector and phi. A vector is electromagnetic vector potential, phi is electromagnetic scalar potential. Substituting the values of B vector and A vector from equations 5 and 7 in equation 4. This is fourth Maxwell equation. Del cross B equal to mu 0 into J plus epsilon 0 delta E upon delta T. In this equation, we put the values of B vector and E vector from these relations. B vector equal to del cross A and E vector equal to minus del phi minus delta A upon delta T. Then we have del cross A equal to mu 0 J plus mu 0 epsilon 0 delta upon delta T minus del phi minus delta A upon delta T. Now del cross A can be written as del of del dot A minus del square A. Here we use the relation A cross B cross C, A vector cross B vector cross C vector, and A cross B cross C is A dot C times B. A dot C means del dot A, which is here del dot A, it is A dot C. A is del vector, B is again del vector, and C is A vector. So A cross B cross C is equal to A dot C times B, which gives this first term. A dot C means del dot A, and times del, which is written initially. Then second term is A cross B cross C is A dot C times B minus A dot B times C. Now A dot B becomes del dot del, that is del square, and C is A vector. So it is del square A vector. So left hand side del cross A can be written as del of del dot A minus del square A, and right hand side is mu 0 J vector plus mu 0 epsilon 0 delta upon delta T minus del phi and minus mu 0 epsilon 0 d2A upon dt square. We solve this bracket. Now we have del square A. Put this minus del square A from left hand side to right hand side. Then it becomes plus del square A minus mu 0 epsilon 0 d2A upon dt square. This is the last term. And minus del of del dot A, it is the first term, del dot A, it is bring to right hand side, then here it becomes minus del of del dot A, and in this term minus del is taken as common. Then the remaining term is mu 0 epsilon 0 delta phi upon delta T. and this term mu 0 j is taken to left hand side, so it becomes minus mu 0 j. So we write this equation as del square a minus mu 0 epsilon 0 d2a upon dt square minus del of del dot a plus mu 0 epsilon 0 delta phi upon delta t equal to mu 0 j vector. Similarly, substituting the value of E vector from equation 7 into equation 1. First equation is del dot E equal to rho upon epsilon 0, and in this equation we put the value of E vector from this relation. E vector equal to minus delta phi minus del phi minus delta A upon delta t. If we put this value of E vector in this first equation, del dot E equal to rho upon epsilon 0, this become as del dot, this is the value of E vector, minus del phi minus delta A upon delta t equal to rho upon epsilon 0, and it becomes equal to minus del dot del phi minus delta upon delta t del dot A equal to rho upon epsilon 0, and we add and subtract here by mu 0 epsilon 0 d2 phi upon dt square. These are the two terms, one is plus and other is minus. We add and subtract this term mu 0 epsilon 0 d2 phi upon dt square. In this way we can write this equation as del square phi, del dot del is del square phi minus mu 0 epsilon 0 d2 phi by dt square plus delta upon delta t del dot A plus mu 0 epsilon 0 delta phi upon delta t equal to minus rho upon epsilon 0. Rho upon epsilon 0 is taken to left hand side, and the other terms of left hand side are taken to right hand side, so their sign change. Equations 8 and 9 represent two inhomogeneous wave equations in terms of electromagnetic vector and scalar potentials A and phi. These inhomogeneous wave equations can be uncoupled by using concept that A vector and phi are arbitrary. We have defined scalar potential A and vector potential A and scalar potential phi. These are arbitrary, and generally A vector and phi are chosen subject to this condition: del dot A plus mu 0 epsilon 0 delta phi upon delta t equal to 0. In this relation, the term in left hand side, it is this term inside this bracket in these two relations. In equations 8 and 9, inside the bracket we have this term del dot A plus mu 0 epsilon 0 delta phi upon delta t. If we put this equal to 0, then these two equations becomes very simple. So this condition del dot A plus mu 0 epsilon 0 delta phi upon delta t equal to 0, this condition is known as Lorentz condition, and if we apply this condition, then above two equations becomes have this form: del square A minus mu 0 epsilon 0 d2 A upon dt square equal to minus mu 0 j, and del square phi minus mu 0 epsilon 0 d2 phi upon dt square equal to minus rho upon epsilon 0. Equations 10, 11 and 12 form a set of equations equivalent in all respect to Maxwell's equations. So these three equations are equivalent to four Maxwell's field equations. First equation is known as Lorentz condition, and these two equations, other two equations, equation 11 and 12, these are wave equations for A vector and phi. wave equations for A vector, that is vector potential, and other is wave equation for scalar potential phi. As speed of light in vacuum c is equal to 1 upon under root mu 0 epsilon 0. So mu 0 epsilon 0 becomes equal to 1 upon c square, and in these two relations, if we put mu 0 epsilon 0 equal to 1 upon c square, then these two equations reduces to del square A minus 1 upon c square d2a upon dt square equal to minus mu 0 j, and del square phi minus 1 upon c square d2 phi upon dt square equal to minus rho upon epsilon 0. And del square A minus 1 upon c square d2a upon dt square can be written as this del square A. Now here we use this rectangle symbol, and this rectangle is, we call it also as del square. It is del square A. This del square, where we use this rectangle, it is known as D'Alembertian. This del square D'Alembertian, it is equal to del square minus 1 upon c square d2 by dt square. So D'Alembertian del square A equal to minus mu 0 j, and other equation is D'Alembertian del square phi equal to minus rho upon epsilon 0. Here D'Alembertian is this rectangle and square. Here two rectangles are formed. Remove first rectangle. So here this del square is known as D'Alembertian. For medium of permeability mu and permittivity epsilon, we must use mu and epsilon in place of mu 0 and epsilon 0. In vacuum or free space, we use mu 0 and epsilon 0. And for a medium of permeability mu and permittivity epsilon, we use mu and epsilon in place of mu 0 and epsilon 0.